Okay, hello everyone, and thank you for listening in. I'm going to give a very brief tutorial here on how to find a data set within the Include Data Hub and push that over to the CAVATICA platform for analysis. These slides, or a full set of slides detailing the steps I'm going to go through here and the R code I'm going to use, are available at GitHub. Feel free to get in touch with me on there. We'll also make these available through the Include Data Hub. So we're going to jump right in and go over here to the Include Data Hub. One thing to note is that if you haven't already connected to CAVATICA from within the hub, you'll need to do that. It will have a connect button here, and you'll need to log into CAVATICA so that the hub can pass data over to the CAVATICA system. Within the hub here, we can look up details about each of the studies. For example, the Human Trisome project here. You'll enter a landing page that contains some information about each of the studies. For today, we're going to go into the data exploration tab here. And more specifically, we're going to jump over to the data files tab. And you can see here, there's about 11,500 data files here. And we're going to build a query. So, for example, I may be interested in metabolites that are differential in the plasma of individuals with trisomy 21 compared to euploid controls. So how do we do that? How do we identify that data? So first of all, I happen to know that there is a data set, a metabolomics data set within the Human Trisome project. So we're going to go over here to these filter tabs, and we're going to choose the study code for HTP right here. We're going to hit apply, and then that places it over, or transfers it over to this study builder. And then we're going to go to the data files and choose a data category here. We're going to choose metabolomics, hit apply. And so we've now filtered down to 418 files, which are from the HTP study that are metabolomics. These are LCMS metabolomics. And so that's it. That's how we drill down to a particular data set. You can save this set of files and give it a useful name. You can also save the filters that you build so that you could perhaps come back later and check if there was an additional metabolomics data added to this. So now we need to select these files. By default, that selects just the items on this page. So make sure you hit select all results. Have all of the items selected, and then we will hit analyze in CAVATICA. And I've already copied these over to a project, so I'm not going to do that here, but if you needed to, you would then select a project here that's available in CAVATICA, or create a new project, and then you would hit the copy files button. So now we go over to that project in CAVATICA, and if you look, and this is the dashboard or the landing page for the project itself. If you look in the Files tab, we now see that those files are here. There's 418 of them. And so we have successfully transferred files over from the Include Data Hub to the CAVATICA platform. They're actually not physically copied, but they are linked in such a way as you can access them. So now what we're going to do is create an interactive analysis. So to do that, we go to this Data Studio tab. And I've already got created one running here, but normally you would select create new analysis. You would give it a useful name. You can do these in a Jupyter Lab environment. And here we're going to use RStudio. You can change the defaults if need be for more resources, although that will cost you more, and so on and so forth. And then you would hit start. So I've already done that to save a little bit of time. We have an analysis already running. And this code here is what is also available on GitHub. This is my R script that we're going to run right now. If this is the first time, again, you'll have to install all these packages, but here we're just going to load these packages that we need for this analysis. And I did that to save time. We're going to define some colors here, and then we need to get a list of the files. And so this is where the files live in the project. This is the location of them. And then we're going to restrict that, make sure that we only look at metabolomics files. And so what we have now is a list of 418 file locations. This is one file per individual that had these measurements made. And so what we need to do is concatenate those files. That should take us about 18 seconds if you've already accessed the files previously. And all we're doing here is reading each file individually and concatenating them together. Great, so that takes about 20 seconds. And what we have now, and we need to build this data in such a way as we can use it for linear regression modeling. That's the test we're going to run here that tests for differential abundance of each of these metabolites between the trisomic samples and the euploid controls. And so we're just going to select the values that we need here, which is all we need is the lab ID, the metabolite that's being measured, and this value here, which is the relative abundance value. And normally we would bring across and join to demographic and clinical data here, such as T21 status. I'm going to cheat a little bit here to save some time. I can decode and add that variable for trisomy 21 status from our sample identifiers here. So we've added that. We now have a variable that says whether they were euploid controls or individuals with trisomy 21. We're going to remove some outliers very quickly. In this case, it doesn't remove too many values. Normally we do a bunch of other checks here to make sure that this data fits the assumptions of the linear regression model. I know that this data is good. And then we're going to nest this data at the analyte or the metabolite level. That gives us 174 rows. That's 174 models that we're going to run with this linear regression. And all of the other data is packaged up in this nested data frame here. Very efficient way to carry this out. Okay, so we now have that data packaged up, and we're going to run this linear regression model. And what we use is this map function, which allows us to run that model across individually across the 174 metabolites. Here's the formula for the model. So we're going to take the log2 of the relative abundance value as the outcome variable and the karyotype or trisomy 21 status as the predictor variable. We're going to run that, and then we're going to use this broom tidy function, which extracts the results in a nice format for us. So let's do that. We'll run this. It usually takes about 1 second. Great, that's done. And so what we have now is a set of 174 linear models. We can see them in this fit column here. And then we have the extracted results from each of those models in a small table, again, nested per metabolite. So now we need to expand that back out and extract the results in a nice format that we can use. And this is a very quick demonstration of how to do that. So now what we have is the log2 of the relative abundance in this case, the euploid controls and the trisomic samples with the fold change, and we have a p-value. Because we've carried out 174 different hypotheses, we need to do some multiple testing correction. We're using here the Benjamini-Hochberg or FDR approach. You can see we now have an adjusted p-value here. And then we're going to do a little bit of quick formatting to tidy things up. And so that's our final results that we can now use to examine which metabolites. And you can see these are sorted by p-value. So these are the top most significant metabolites listed here. We can also visualize that in a more summary format using a volcano plot. Zoom so we can see that. So that's just showing us the log2 of the fold change up, things that are up in trisomy 21, things that are down, versus the confidence level or the p-value. We can save these files out and they will become available in that Files tab. We could also make an interactive version of this plot, which allows us to hover over the points and read or identify what the names and the fold changes are of each of those. So we probably want to look at some of the actual data. So we're going to take that data that we built for the regression model so that we're using exactly what the model looked at. We're going to filter to those top 2 metabolites, and we're going to make a plot here. And so you can quite clearly see that the top 2 metabolites by p-value here have, on average, an increase in the plasma of individuals with trisomy 21 versus the euploid controls. So hopefully that gives you a good sense of what one can do by finding data sets in the Include Data Hub, pushing them over to CAVATICA, and at least a quick sense of how to do that analysis. I'm happy to answer any questions if people have further questions on that. Thank you for listening.